Okay, everyone. So thank you so much for your interest. I'm really glad to see you all here. Before we start, let me ask you one quick question. How many of you here do have studied or have some experience with quantum mechanics and quantum computing? Nice, nice. Okay, well, more than I expected, actually. So, all right, no problem if you don't have any experience with that. Actually, that's what I was expecting. I just wanted to, calibrate a little bit. All right, so my name is Mário. I am a software engineer in Red Hat. I also happen to be a physicist, so that's where I know all this cool stuff. And today I want to talk about this really interesting paper that came out by the end of last year, where the authors showed that whenever you have a game, anything that can be framed as a game from game theory, if you allow the players to have access to quantum resources, then you're going to have different Nash equilibria, which will enable higher social welfare, which is really nice. It means that everyone is getting more out of that game. There is a better solution, and it's being, things are going a much better way in there. And plus, they analyze two different scenarios. One where the players have direct access to the quantum resources. So that would be like, each player has, say, a physics laboratory in their garage. And also another more realistic scenario where the players have access to the quantum resources through in a mediated manner. So that would be like renting time in a quantum computer in the cloud. And the cool thing is all these benefits happen in both scenarios. And the scenario where you're renting computer in, the scenario where you're renting time in a quantum computer over the network is what you can do right now. Like you can do that in, say, IBM Quantum. Like any of you can, right after this talk, go and create a free account there. And so it's very feasible. I really want you guys to leave this talk knowing that what I'm going to talk about is not for the near future, it's not for 10 years. It's feasible right now, okay? So yeah, really cool, right? So first, I'm going to remind you guys a little bit about what non-cooperative games are. Then I'm going to talk about how you can enable quantum resources in this, this scenario. Then I'm going to go over the advantages that you get from doing that, and then we're going to find the conclusions. All right, so non-cooperative games. So what is a game in game theory? It's this situation where you have, people or systems, maybe even computers, taking decisions. So we will call them players, right? So each player receives a question, and based on that question, they have to make a decision and output an answer. So the players don't know the questions that went to the other players, and they don't know the answers that the other players are giving, right? So they're kind of like in the dark about this. And finally, there is some outcome out of their joint decision overall. So there are some winning conditions, and depending on how each one played out, something different is going to happen. Now, to make this a little bit less abstract, the one very mundane example that you can think of is a crossroad. So imagine you have a crossroad and you have two cars coming in. Now, each driver has a decision to make. Do they stop their car or they keep going? So if both of them go, they're going to crash their car. It's going to be terrible. It's a really negative outcome. So both of them would get like, I don't know, -5, and, for the both of them. If, on the other hand, they both stop, they're just going to sit there, get late to where they needed to go. So it's still a negative outcome for both, but less negative than crashing the car. On the other hand, the perfect outcome would be for one to wait and the other to go. Then whoever went gets a positive outcome, and the other just has a neutral outcome, for example. Now, when you have a game, the players are going to try to maximize their payoff, and this is going to lead to different answer strategies. In the crossroad example, this would translate to how often you decide to go or to stay. If you try to go like every single time, there is a higher chance you're going to crash your car. On the other hand, if you decide to stay and never go, you're never going to get where you need to go, so that's not good either. So it's somewhere in between. Like you have to, if you think about the probability that you should make each decision, there's going to be an optimal spot somewhere in between the two. Now these optimal points are called Nash equilibrium. And they are like the strategies that usually the collective behavior converges to because they are the optimal things to do. And finally, the last thing I have to tell you about is what the social welfare is. So the social welfare is just the average payoff for a given strategy. Now it's more interesting to calculate that at the Nash equilibrium because those are the optimal points, right? So yeah. Okay, so now, still in the classical regime, you can add one more ingredient to the situation, which is to allow the players to have a shared correlation. This would be like putting a traffic light in your crossroad. So in this situation, you are going to have like something else, maybe another person, maybe a computer, maybe some kind of system in between. So there's that red guy there. And this guy is going to be exchanging information with each of the players. Now, the players don't exchange, they only are allowed to exchange information with this coordinator. And because of that, he can maybe coordinate people and things fare out better. Like, for example, if people follow what the traffic light is showing, like they don't crash the car and they don't have to sit too much time idly. So when you allow this into your system, you're going to have access to new and different Nash equilibrium points. And usually, you can show that they're going to allow these new points are usually going to have higher social welfares. All right. Now, how do we put quantum resources into this? So in this, how can I say this? So to allow a quantum resource into the game situation, you have to allow for a quantum correlation in the place of the correlator. So in the theory, that's the ingredient that you have to swap by a quantum ingredient. It's the shared correlator. Now let's take a step back. I'm not going to get into too much detail, but I will try to give you a slight notion of what's happening in the background when you do this. So if you think of a classical bit, you have just your Boolean variable that can be either true or false. Now, when you swap that by a quantum bit, or a qubit for short, you're going to swap those, that Boolean variable by a 2D unit vector. So you're going to be leaving a discrete space, or you're going to be leaving it behind the Boolean algebra, and you're entering the realm of linear algebra and continuous systems. So you can imagine that when you do this, the mathematics behind all the optimization and the Nash equilibrium points, it's going to be a different landscape. So of course, if you have a new landscape, you're going to have new Nash equilibrium, and of course, you're going to have new social welfares in those Nash equilibrium. So this is what's happening behind, mathematically speaking. Now you can do this two ways. The first is the direct access scenario where your players have, I don't know, maybe a physics laboratory in their garage. And there they can prepare, say, a system of multiple qubits. And after they prepare it, they share one particle with each player. Okay, so picture this. They have a super nice garage. There you prepare a system of 3 particles, and then you shoot 1 particle to each player. Now, in this scenario, you don't have really a mediator there. You don't have like a traffic light or, say, a police officer that's correlating people. And this leads directly to an enhanced privacy because you don't have exchange of information with the players. Or better said, when you had the shared correlation, you would have a bidirectional channel of communication between the players and the correlators. But now, you only have a one-way channel. So you cannot acquire information about the players by doing this. So the players have their privacy preserved. Another really nice thing is that quantum systems don't have friends or enemies. So if you picture a crossroad with a police officer, well, maybe he has a neighbor that he doesn't like, or a really nice friend, and every time that neighbor or that friend goes to the crossroad, he will either let him press through directly or hold them for an hour on end. So when you're using a quantum system, this is just not possible. So these are directly out of the box, two really nice features of using this. Now the next way that you can allow players to have access to quantum resources is through this mediated access. And this is really nice, guys. So this is the scenario that you would have when you're renting time on quantum computers through the cloud. So the players themselves, they don't receive any particle, but someone else before them, further away in the network, receive it and do their magic, and then just exchange classical information with them. So yeah, so in a real, to make this less abstract, you can picture somewhere inside of IBM there is a quantum computer and people around it, and so they will be handling directly the quantum system, and then they're gonna just send, I don't know, stuff through SSL and through the internet to the players. So this is a really practical scenario. This is the thing that I want to get you guys excited about. Any of you can do this right now, okay? Yeah, so this is the second scenario. Now that we know how to let our players use quantum stuff and quantum toys, what do we get out of it? So the the most important question that must be on your mind right now is, do these quantum resources enable higher social welfare? And well, I gave you the answer already, it does. So the most important result, at least, there's a theorem in that paper where the authors, they show that there is this order of inclusion between these four scenarios we saw. So all the Nash equilibrium from the classical game without any correlation, so this set of Nash equilibria is going to be contained in the Nash equilibria of the scenario where you have classical shared correlation, which in turn is going to be contained in the Nash equilibrium of the direct access scenario, which finally is going to be contained inside the Nash equilibria of the mediated scenario. And now, since you have inclusions, since it's very logical, right, that when you hop from each scenario to the next one, you can only increase your social welfare because you're getting more points, new Nash equilibria, but you still maintain the older ones. So you're bound to increase the overall social welfare. So yeah, this is a pretty strong result. And very interestingly, the scenario where you have mediated access is actually the one with the highest possible social welfare. So really another right thing to notice. But all of this is very theoretical. It's a theorem. They show it's not less than. So the next question we might be asking is, well, how big is that difference? And well, they answered this question too, but they do numerical calculations for specific games and more specific scenarios. But the results are very encouraging. So what they do is they search in these quantum the space of all quantum states for the best Nash equilibrium and the social welfare on it. They do the search using a technique called semi-definite programming. They also use really smart tricks to reduce the search space. And they look to 3 specific games. And these games, they can be parameterized in the reward values, okay? So this is the results they get to the first game. What I want to call your attention here is the gap between the dashed yellow line and the other curves right there. So the dashed yellow line is the worst case. So that is the classical game without any kind of correlation. And the other curves is the social welfare in the other scenarios. So you can see that if you go too farther to the right or to the left, there's not much gain. But in the middle of that V shape, it's pretty noticeable, right? It's something, So they did this for this first family, and the overall, the overall result holds for all these families. So this is for the second family. That gap is still pretty big. Third family, same happens. So numerically, they show that it's a very noticeable thing. It's quite a bit. It's significant. It's not just a little bit. All right. So let me wrap up all of this thing. So we have seen 4 scenarios with different correlations. We saw the classical game without any correlation. We saw the classical game with classical correlations. We saw the direct access to quantum resources, and we saw the mediated access to quantum resources. And we saw that we have an increasing order of the social welfare as you hop from one to the other. We also saw that the enhancement in social welfare can be quite significantly, and also we saw a few other benefits of when you have quantum resources. So when in the direct access to quantum resources, you get the benefits in your privacy and preventing collusion. And in the mediated scenario, you have the best overall social welfare. And plus, it's the feasible scenario. It's the scenario anyone here can do right now. I want to make a bold statement here. The mediated scenario is practical right now. It's not something for the future. So you guys can go and create a free account in IBM Quantum and try to apply this to any problem you might be thinking. And this is what I really wanted you to get out of this talk. If anyone loses sleep this night and keeps thinking, wow, come on, what can I frame as a game in game theory? Oh, that's that really nice problem that I struggle every day in my work or in a daily basis. Then I want you guys to lose some sleep and come up with nice ideas on how to apply this to that. So here's some food for thought. If you have any kind of processing queue, maybe people competing over resources in a platform that you develop, or maybe any kind of daily problem like a crossroad. If you manage to formulate that as a game in game theory, then there's mathematical proof that if you enable quantum resources, you're going to get a better solution, better social welfare. Like this will help you. All you have to do is frame it as a game, all right? And if you cannot think of any problem that you can frame as a game now, well, keep on the lookout. I'm sure you're going to come up with something. And finally, this whole paper, at least for me, it was really inspirational that they, really, even though it's a very technical result, it's really tied to how people are using the technologies, and it's really focused on the highest social welfare for the end users. So I also wanted to make a bold statement out of this. I want to invite you guys to do this reflection. How is the technology that we make being used? Can we make something for it to bring more social welfare? And with that, I want to thank you much for your attention. And if you have any questions, I'll be happy to answer them. Yeah, the microphone is on here, right?
In the mathematical model that you have showed, it has always seemed like it was necessary for all contenders to have access to the quantum resources. Is that correct? Does the same still apply if only a sub number of the players have access to those resources?
You mean if some players have access and the others don't?
Yeah, exactly.
Okay. Well, this does still apply. Probably you will have, a lower social welfare, maybe. But yeah, I mean, I think you can still have an increase. Maybe not as big as if everyone had, but you still probably have any, better scenario there.
Did I understand it right that the privacy part for the direct access is not available in the mediated case?
I'm sorry, I couldn't hear you very well.
You said that in the direct access with the quantum scenario, you have an increase of privacy because of the direct access.
Yeah.
Is this privacy also available in the mediated case? Because you have a mediator between, so
Right. Well, not really, because if you look at this picture, so if you cut off like one branch here, it's going to be pretty much the same scenario that you had here. Like if you cut one branch, after oops, oh my gosh, what a mess am I making? So after this point, so from here onwards, it's the same scenario, so you lose that in the managed scenario.
okay. A second question.
Sure.
Is it right that it's like everything where you have to decide on priorities? You can use this features here?
Pretty much. Usually, like most of the examples I saw of things being framed as games are these situations where you have like people or things competing for the same resource. So this is the most classical way. So yeah, I really think that even though at first it might seem hard, like maybe you give it some thought, and after a while you can come up with a way of framing it as a game. So it's pretty much like, I'm not an expert in game theory, but that's my gut feeling.
Just curious, are there like specific practical examples that you have seen this to make an improvement?
No, I have not. There aren't any, yeah, unfortunately. Maybe. So this paper is pretty recent. I think it came out like on November last year. So maybe there's things coming right up. I hope so. But yeah, I haven't seen so far, to be honest. All right. Well, if there's not any more questions, I just want to thank you guys again. Yeah. If you like see me out there in the corridors and want to chat, feel free. I'll be glad to exchange a few ideas. You can find. I didn't put any of my social media there because I don't really have any. But you can find my email in the link to this talk in the pre-talks platform, and I'll be glad to keep in touch. And all right, so thank you so much.